In this video, we're going to talk about the equilibrium constant. So in the last few videos, we kind of introduced equilibrium from a qualitative perspective, where we looked at what the relationships are between products and reactants and how stoichiometry can be used to work things out in terms of the number of moles or the molarity of products and reactants at equilibrium. And we also looked at equilibrium from a qualitative sense in the perspective of that the rate of the forward is equal to the rate of the reverse, that the concentration at equilibrium, the concentrations become static, meaning that they kind of become constant, but that the reaction is still dynamic, meaning that things are still moving back and forth. It's just that because the rates are equal, the concentrations remain constant. So what we're interested in now is developing a quantitative sense for the concentrations at equilibrium. So the equilibrium constant is going to allow us to not only predict the relative amounts of products and reactants at equilibrium, and we'll talk a little bit about that, but it's also going to allow us to actually calculate the amounts of products, the concentrations of products and reactants at equilibrium. So let's look at an example and let's start to see how we can define this idea of an equilibrium constant. So if we take a simple equilibrium, like N2O4 is in equilibrium with 2NO2, and these are gases, what we can do is we can say, we know a few things. We know that at equilibrium, the rate of the forward is equal to the rate of the reverse. And we can write rate equations for the forward and the reverse. So the rate for the forward is going to equal K forward. And we're basically just assigning a rate constant, whatever it is, for the forward, and a rate constant, whatever it is, for the reverse. So we call that K forward, and we call the reverse K reverse. So we say K forward, and then we can take the concentration of N2O4 for the forward, and we put that to the 1. Now remember, these forward and reverse reactions are elementary reactions because they are basically mechanistic steps in this backward and forward reaction. So we can use the stoichiometry here. And we can say that the rate of the reverse is equal to K reverse times the concentration of NO2 squared. And so at equilibrium, since the rate of the forward is equal to the rate of the reverse, we can set these two equations equal to each other. So we can say that K forward times the concentration of N2O4 is equal to K reverse times the concentration of NO2 squared. And if we reorganize this, we can get the K's on one side and the concentrations on the other. So if we do that, we can have K forward over K reverse is equal to the concentration of NO2 squared divided by the concentration of N2O4. And this is how we can define an equilibrium constant. So if we take these two rate constants and we wrap them up, so if we basically do this division, we can turn this into one constant called the equilibrium constant. And the equilibrium constant is the rate constant of the forward divided by the rate constant of the reverse. So big K is equal to K forward over K reverse. And this is going to be equal to the NO2 squared divided by the concentration of N2O4. So that's how we can define this thing called a rate constant. So the ratio of the forward rate constant to the relative to the reverse rate constant gives us an idea for what the ratio of the products to the reactants will be. So let's kind of think about that in a little bit more detail. So what I just said was basically that K forward over K reverse is proportional to the amount of products over the amount of reactants. And so let's think about some of the implications of that. So let's say if K forward is much, much greater than K reverse. So if K forward is much, much greater than K reverse, what does that mean if we have Kf over Kr is equal to the concentration of the products over the concentration of the reactants? And so what this would mean is that K would be a large value. Let's say something like greater than 1,000 or something like that. Well, what this is going to mean is if K forward is very large and K reverse is relatively small, or big K is a large number, that means that we're going to favor products. And that makes sense, right? So if you think about this, if we're favoring the forward, so if the forward is much larger than the reverse, the rate of the reverse, the forward is going to dominate, and we're going to have more products at equilibrium than we are reactants, because the products, in essence, are going to, when this reaction sort of settles down, we're going to wind up having a preference for the products, because the forward is so much faster than the reverse that it's going to allow for the products to build up relative to the reactants. And we can look at the opposite case, where if we have K reverse is, if we have K reverse is larger than K forward, and so in this case, Kf over Kr is equal to the concentration of the products over the reactants. And so again, let's say in this case K is small, and this would be something like less than 0.001 or something like that. These are arbitrary numbers that I'm making up. 1,000 and 1,000th is just sort of arbitrary. These equilibria are on large spectrums. These numbers can be very large or very small, kind of depending on the equilibrium and what's going on with it. So in this case, what we have is we have a relatively small forward rate constant relative to a very large reverse rate constant. So this is going to favor more reactants relative to products, because in this case, the reverse is going to allow for the products to build up relative to the reactants building up. So this is going to favor the reactants. And then if we have the case where, K forward is approximately equal to K reverse. So let's say that K is somewhere between, like 100 to, 0.01 or something like that. Some reasonable numbers close to 1. This means that K forward over K reverse, and so in this case, K would be close to 1, or about, from 100 to 100th. So in this case, the products and the reactants are going to be in a mixture. So this is going to favor a mixture of products or reactants where both are going to be sort of equally weighted. So we're going to get about the same amount of the products and the reactants. And again, this doesn't take into account the fact that one of them is squared. It's just a rough estimate for what is sort of taking place in the mixture. Yeah, and so the idea here is, and the key thing is that the equilibrium constant is a this gives a its magnitude gives a relative estimate for the preference of products versus reactants in the equilibrium mixture. So like we said, if K is large, we're going to favor products. If it's small, we're going to favor reactants, and if it's sort of intermediate, we're going to favor a mixture of products and reactants. And at this stage, don't be too overly concerned with the numbers. Just have the idea that, as like for example, a lot of students get worried about at what number does it favor products versus what number does it favor reactants, and at what number is it relatively equal. That's not the idea here. What it is like, let's say for example we gave you a question where we gave you 4 values of K, and we said which one of these 4 would have the highest preference for products in the equilibrium mixture. Well, what you would do is you would pick the highest value of K out of those 4, right? So this is somewhat relative, you know what I'm saying? It's not necessarily an absolute black and white cutoff. It's more along the lines of, you kind of can see now that we're setting up a spectrum here, and as K gets larger, you're going to favor products. As K gets smaller, you're going to favor reactants. Okay, so now let's talk about how we can write a general expression for K. So in the last one, we had N2O4 goes back and forth with 2NO2. And when this was all said and done, we said that, well, big K was equal to the concentration of NO2 squared divided by the concentration of N2O4. And, this is always going to be how it's going to be, because when you set this up, that equation where we had K forward is equal to K reverse, because the rates are equal, the math is always going to leave the products on top and bring the reactants down on the bottom. So we can set up a general expression. So the general expression that will be set up when we're writing these equilibrium equations is as follows. So if we have something like a plus little b goes to little c plus little d, and these little a's are the stoichiometric coefficients, and the a is the compound, right? So this would be, like for the CO example that we had before, this would be the CO in the water, and this would be the CO2 and the H2. And then the little stoichiometric coefficients would be the 1, 1, 1. So the way that this would get set up is we would write big K, which is our equilibrium constant, and then we would have a general expression where we would have the products to their stoichiometric coefficients, and we'll have beneath that the reactants to their stoichiometric coefficients. So we'll have a and b little b. And so we could do this for any expression. So we're actually going to practice this a little bit in a few seconds, but there's a couple of caveats that we have to talk about. And one thing is, what do we do with heterogeneous mixtures? So one of the caveats that we have to think about is when we have a heterogeneous mixture. And there's a problem with just using that general expression all the time. And that is when we have something with pure solids or pure liquids. And these do not appear in the equilibrium expression. So you're going to leave out anything that has a solid or liquid phase label gets left out of the value for K. So let's take a look at an example, and I'm going to explain to you why this is the case in just a second. So, for example, if we have calcium carbonate solid is in equilibrium with calcium oxide solid and carbon dioxide gas, you would be tempted to write, well, okay, I have K is equal to the products, calcium oxide, times the concentration of CO2 divided by the concentration of calcium oxide. And, you would think that this would work out just fine because, these are all compounds and that would be that. However, there's a problem. The problem is that it's the concentration of a solid. So it turns out that the concentration of a solid is actually just a constant. So if you think about it, so with, for example, calcium oxide solid and calcium carbonate solid, concentration is the same thing as moles per liter, right? And in the case of a solid, we can actually sort of reconfigure this a little bit. This is actually going to be proportional to, we can use the molecular weight to get us over to grams, and we can convert liters to milliliters. And for solids, this is the density. So the concentration of a solid is actually dependent on the density, which is a constant. Right? So we learned this in chapter 1. The density of any solid material is a constant for that material no matter where it is. So the concentration of a solid will never actually change because the solid, if you think of it this way, right? So a solid, as you increase the amount of mass, the volume of that solid is going to increase, and it's going to increase according to the density. So we don't, these solids, and the same thing goes with a liquid. When you increase the amount of water, the mass of the water, or the moles, because mass and moles are related by the molecular weight, the volume is going to increase, and it's going to increase according to the density of 1 gram per mil. So this is a constant, and the constant doesn't need to be put into here. The constant is just going to actually factor out. And what winds up happening is that the constant gets wrapped up into K. So the best way to think of this is that really what you have here is you have a K, which is the Kf over Kr, and then you have the concentration of calcium carbonate, which is its density essentially, and the concentration of calcium oxide, which is its density, is proportional to the concentration of CO2, and this entire thing gets wrapped up into the equilibrium constant. So the quote-unquote concentration of solids and liquids is a constant and it gets built up into the equilibrium constant K. Now let's look at why CO2 is actually different, right? So for example, CO2 in this case, this is a gas, and in this case, we would collect this gas in some kind of container. It could be a rigid container like this. And so the concentration can actually vary because the volume is fixed. But as we change the number of moles, the volume of that is not going to change, right? The volume of the box is not going to change. So the concentration will change as the number of moles changes for a gas. But for the solid sitting at the bottom, for the little bit of solid that's sitting down there, its volume and its number of moles are going to be always proportional to each other, even in the larger volume of this fixed container. So that's why CO2 is left on this side, but the calcium carbonate and the calcium oxide are not. And the proper way of doing this would be to just say that K in this case is going to be equal to the concentration of CO2. And so these do not appear in the actual equilibrium expression. So let's actually do some practice with this and take a look at some examples. So this is lecture problem 2, and what we're going to do is we're going to start working on doing some examples of writing equilibrium equations. So in this case, we have our first equilibrium where we have CO gas plus H2O gas plus CO2 gas plus H2 gas. So these are all okay. These are all gases, so we're not going to be leaving anything out. So it's going to appear as is. And then we're going to get started. So what we're going to do here is we're going to write K, which is our equilibrium constant, is going to be equal to the concentration of CO2 to the 1, which is its stoichiometric coefficient, times H2 to the 1, which is its stoichiometric coefficient, divided by CO to the 1, times the concentration of H2O to the 1. And so that's how you would write the equilibrium equation for that. Now here we have an interesting one. We've got some solids, and we've got some gases. So in this case, we're not going to include anything that's a solid, but we are going to include things that are gases. So in this case, K would be equal to the concentration of H2 to the 4th, which is its stoichiometric coefficient, divided by the concentration of H2O to the 4th, which is its stoichiometric coefficient. And on the bottom, we have another one where we have water as a liquid. And so this is going to equal K. K is going to equal the concentration of H2O, the gas, but we're going to exclude the liquid because the liquid is a pure liquid and its concentration is a constant, so that gets left out. So that would be how you would write these. One thing I'd like to mention is that if you have the phase label aqueous, that most certainly would appear also in here. So gases and aqueous appear, but not solids and liquids. Those don't go in there. So that is an introduction to how we work with what the equilibrium constant is and how we write equilibrium expressions based on the definition of an equilibrium constant.